Area bounded by the curve and the y-axis. Welcome, everyone. Before we dive into today's new topic, let's take a moment to reflect on what we have already mastered. In our previous lesson, we focused on calculating the area between a curve and the x-axis. You might remember that in those problems, we used vertical strips to sum up the area. However, as we move forward, you will find that mathematics isn't always that straightforward. In many mathematical problems, and even in many real-world engineering or physics scenarios, it can be much more convenient, or sometimes even absolutely necessary, to calculate the area relative to the y-axis instead of the x-axis. Now, you might be wondering, when should we make this switch? The key lies in the equation of your curve. We use this method when the curve is more easily expressed as x being a function of y, rather than the more common form where y is a function of x. In the next few slides, I will show you exactly how to visualize these horizontal strips and the specific formula you'll need to use to solve these problems. Conceptualizing the area via horizontal strips. Now that we understand why we might need to look at the y-axis instead of the x-axis, let's dive into how we actually visualize this. In our previous lesson, we used vertical strips to find the area under a curve. But to find the area bounded by a curve and the y-axis, we need to shift our perspective entirely. We are going to switch from vertical strips to horizontal strips. Let's walk through a step-by-step visualization to see how this works. First, imagine a single, very thin horizontal rectangle, which we call a strip. This strip is positioned between the y-axis and our curve, which we can represent as x equals g of y. Next, let's look at the dimensions of this strip. The width of this strip is the horizontal distance stretching from the y-axis over to the curve. This distance is simply the value of x. Now, consider the height. Since this is a horizontal strip, its height is an incredibly tiny, or infinitesimal, change along the vertical y-axis, which we denote as di. Because this is just a tiny rectangle, we can find its elementary area, which we call dA. To get this area, we simply multiply the width by the height. So, dA equals x times di. Finally, to find the total area, which we call A, we don't just want one tiny strip, we want the whole region. To do this, we sum up or integrate all these infinitely thin strips, starting from our lower boundary, which is y equals c, and continuing up to our upper boundary, which is y equals d. This concept of summing up horizontal slices is exactly what leads us to the formal mathematical formula we will see on the next slide. The mathematical formula. Suppose we have a region that is bounded by a curve, which we can express as x equals g of y, the y-axis, and two horizontal lines, or what we call ordinates. At y equals c and y equals d to find the total area, represented by the capital letter A, we use a definite integral. This integral starts from our lower boundary, c, and goes up to our upper boundary, d, integrating x with respect to di. But as we noted in the previous slide, we want our integral to be entirely in terms of y, since we have already defined our curve such that x is equal to g of y. We can simply substitute g of y into our integral in place of x. This gives us our final working formula. The area A equals the integral from c to d of g of y with respect to di. This is the precise formula we will be using for all our calculations moving forward. Now that we have visualized those horizontal strips, let's translate that visual concept into a formal mathematical formula. Step-by-step procedure to calculate area. Now that we have understood the concept of horizontal strips and the mathematical formula behind them, let's talk about how you can actually approach these problems in an exam or a tutorial. I want you to follow a consistent, 4-step procedure to ensure you don't miss any details. First, step 1. You need to express x in terms of y. This is a crucial step. You must ensure the equation of your curve is written in the form x equals g of y if the problem gives you the equation in the more familiar form, y equals f of x. You cannot proceed with the integration yet. You must rearrange the equation to isolate x on one side. Second, step 2. Identify your limits. Since we are integrating along the y-axis, you need to determine your lower limit, which we call c, and your upper limit, which we call d. These limits are found on the y-axis and are defined by the horizontal lines that bound your region. Third, step 3, set up the integral. Now you take the function g of y that you found in the first step, along with your limits c and d, and plug them into our formula. You will write the integral from c to d of g of y with respect to die. Finally, step 4, integrate and evaluate. This is where you perform the actual calculus. You will integrate the function and then apply the fundamental theorem of calculus by substituting your upper and lower limits to find the final numerical area. To see this procedure in action, let's move on to our next slide, where we will work through a practical, illustrative example involving a parabolic reflector. Illustrative example. Now that we have understood the theory and the formula, let's apply it to a practical, illustrative example. Imagine we are looking at the cross-section of a parabolic reflector, the kind of shape you would find in a satellite dish or a car headlight. Suppose the inner boundary of this reflector is modeled by the equation y squared equals 4x. Our task is to find the area of the region that is bounded by this curve, the y-axis, and the horizontal lines y equals 0 and y equals 4. Let's break down the solution using the 4-step procedure we just reviewed. Step 1, we must express x as a function of y. We start with our given equation, y squared equals 4x. To isolate x, we simply divide both end sides by 4. This gives us x equals y squared over 4. Therefore, our function, which we call g of y, is y squared over 4. Step 2, next, we identify our limits of integration. The problem explicitly states that the region is bounded by the horizontal lines y equals 0 and y equals 4. This means our lower limit, c, is 0, and our upper limit, d, is 4. Step 3, now we set up the integral. Using the formula we learned in the previous slide, we place our function and our limits into the definite integral. This gives us the integral from 0 to 4 of y squared over 4 with respect to y. Step 4, finally, we integrate and evaluate. To simplify the calculation, let's take the constant, 1/4, outside of the integral. Now, we integrate y squared with respect to y. Applying the power rule for integration, we increase the exponent by 1 and divide by that new exponent, which results in y cubed over 3. Now, we apply the fundamental theorem of calculus by substituting our limits. We plug in the upper limit, 4, and subtract the result of plugging in the lower limit, 0. 4 cubed is 64, so we have 64 over 3 minus 0. When we multiply 64 over 3 by our constant, 1/4, we arrive at our final answer, 16/3 square units. It looks like a lot of steps, but if you follow the process, it is quite logical. However, as we will see in the next slide, there are a few common mistakes you should be careful to avoid. Common mistakes to avoid. First, watch out for using the wrong variable of integration. A very frequent mistake is accidentally using x instead of y when you are calculating the area relative to the y-axis. Always remind yourself, since we are working with the y-axis, our strips are horizontal, which means the thickness of each strip is y. If you see x, you are likely looking at a vertical strip for the x-axis. Second, be careful with your limits of integration. I often see students mistakenly using x-axis intercepts as their limits. Remember, because we are integrating with respect to y, your lower limit, c, and your upper limit, d, must be values found on the y-axis. Always check your boundaries to ensure they are y-coordinates. Finally, do not forget the importance of rearranging your equation. A major error is attempting to integrate an equation like y equals f of x directly with respect to y. This will lead to an incorrect answer. As we saw in our example with the parabola, you must first algebraically solve the equation for x so that you have x expressed as a function of y. Now, before we wrap up and look at our final summary, I want to pause and discuss some common pitfalls. Even if you understand the concept, it is very easy to make a small error that changes your entire result. Keep these 3 points in mind, and you will avoid the most common traps in these types of problems. Key takeaways. First, let's talk about orientation. Remember, unlike our previous lessons where we used vertical strips to find the area relative to the x-axis, when we are calculating the area relative to the y-axis, we must shift our perspective and use horizontal strips. Second, regarding the formula. The area, denoted by a capital A, is equal to the integral from the lower limit c to the upper limit d of x, with respect to die. It is absolutely crucial that you express x as a function of y before you begin your calculation. Third, keep a close eye on your variable of integration. Since we are integrating with respect to y, your limits of integration must be y-coordinates, the horizontal boundaries on the y-axis, not x-coordinates. Finally, a helpful tip for more complex shapes: look for symmetry. If you notice that the region is symmetric about the x-axis, you can simplify your work by calculating the area from y equals 0 to the upper limit d, and then simply multiply your final result by 2. All right, we have reached the end of our lesson. Before you move on to your practice problems, let's quickly recap the key takeaways from today's session to ensure you have a solid grasp of the concept. Review these points carefully, and if you can master these 4 pillars, you'll be well prepared for any problem involving the y-axis. Great job today!